So in chapters 1 through 7, we laid the groundwork for the remainder of this course. These chapters dealt with chapter 1, data collection, descriptive statistics, that was 2 and 4, probability, chapters 5 through 7. Chapter 8 started to form a bridge between probability and statistical inference by giving us models we can use to make probability statements about the sample mean and sample proportion. However, now we're going to start to discuss inferential statistics. So no longer descriptive statistics, inferential. The key word there is inference. Yes. It's the process of generalizing information obtained from a sample to a population. So we're going to have estimation. So using sample data to estimate unknown parameters, or hypothesis testing. So the statements regarding characteristic or one or more populations tested using sample data. We're going to do estimation in this chapter and hypothesis testing in chapter 10. Okay, so we're all about using data to estimate something for the future. We're inferencing using our data. First vocabulary word of this chapter is a point estimate. A point estimate is the value of a statistic that estimates the value of a parameter. So this is going to feel like something we've done already. 100% it does. Are you looking for the other box of highlighters? It's in the back. Are you using them in another class? It's going to feel like exactly what we've done before, and it is. So example 1. The Gallup organization constructed a poll in which a simple random sample of 1,015 Americans 18 or older were asked, do you consider the amount of federal income tax you have to pay too high? Of the 1,015 adult Americans observed, 458 said yes. Obtain a point estimate for the proportion of Americans 18 and older who believe the amount of federal income tax they pay is too high. Since we're looking for the proportion, that's p hat. So the proportion is x over n. For us, that means 458 were yeses out of the 1,015. And if you do that math, that's 0.451. That's a point estimate for this proportion. You're like, Ms. Quigley, that's literally just the proportion of the population. I hear you. Yes, that's a point estimate. But our question is, can we conclude that for sure less than 50%, 45% of U.S. population believes that they're paying too much for income tax? Can we make that conclusion? Is it possible that it's higher and or lower than 45%? Why would this be? Why could that this number we have, this estimate, be a little bit off? Because it's stats. Give me more information on what you mean by that. It's a random sample. It's one random sample, right? What if we happen to pick people who were, I don't know. I can't even, what are we talking about? Federal income tax you have to pay is too high. In a tax bracket that can take a lot of deductions, so they don't feel like they have to pay too much. What if it was actually higher? What if it's actually lower? So a question that it comes with for inferential statistics is basically, how confident are you that this is a good statistic? So due to this variability, because our simple random sample may not precisely reflect the population, we need to report a range or interval of values, including a measure of the likelihood that the interval contains the unknown population proportion. So in statistics, we construct this interval for population parameter based on a guess. Here's our guess right in the center, along with what's called a level of confidence. So if you have a small level of confidence, it means we're making a pretty good guess that the actual number is within a few standard deviations away from our guess. But we can guess with higher confidence if we make our error or the amount of wiggle room we have larger. So a lower confidence means that you're not letting you have as much error, and a higher confidence means that you do. Okay? A confidence interval, here's the definition. For an unknown parameter consists of an interval of numbers based on a point estimate. The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted as, we're going to highlight this in a different color if you have one, 1 minus alpha times 100%. Now, it's not really ever going to look like that.
No.
It will actually look like something like this. A 95% confidence level, or level of confidence. We get this because if alpha is 0.05, what is 1 minus 0.05? 0.95, so times 100% is 95%. So you're going to see it written as a percentage number, but we're getting that from 1 minus alpha times 100. 95% confidence interval implies that if 100 different confidence intervals are constructed, each based on a different sample from the same population, so different guesses, then we expect 95 of the intervals to include the actual parameter and 5 not to include the actual parameter. We're 95% confident that our guess is good. To understand how to construct a confidence interval, let's first review what we know about the model that describes the sampling distribution of p hat, or sample proportion. So the shape is approximately normal provided these three things. Number one, that n times p times 1 minus p is greater than or equal to 10. The sample size is less than 5% of the population, that's independence, and that we have obtained the random sample, or the sample randomly. Mu of p hat is equal to mu, and sigma of p hat is equal to the square root of p minus 1 times 1 minus p over n. This is all from section 8.2. I just recopied it here for you. Okay, flip the page over. What we're basically doing in a 95% confidence interval is we are saying that we are 95% sure, or we are sure that 95% of the confidence intervals that we create will include the actual parameter p. So if we look at this image we have here of this normal distribution, 95% of it is in the center. How much is in this tail? And how much is in this tail? Because altogether that's how much percentage? The 5% that's not a part of my 95. So 100 minus 95, 5, split it in 2. We see that let me read this little blurb. The 1.96, if you see this number, comes from the fact that z sub 0.025 is the z value such that 2.5% of the area underneath the standard normal curve is to the right. Look at your pink pieces of paper right now so you can understand where this number came from. Can you find in the table, not on the sides, in the table, the following number on your P chart? Can you find this number in the area, 0.02500?
Yep.
What is the z-score that makes that number? Negative 1.96, and that's to the left. So flip that over, and to the right, it would be positive 1.96. Correct? So 0.975 is 1.96. So we have the z-score, 1.96, that is the z sub alpha for us. 95% of all the sample proportions are within this 1.96 times the standard deviations away from the guess that we have. So we get this interval here, which is 1.96 times the standard deviations below and 1.96 times the standard deviations above our statistic. That creates our confidence interval. So again, it's like the point estimate plus or minus the margin of error. Point estimate plus or minus the margin of error. Whether a confidence interval contains the population parameter depends solely on the value of the sample statistic. Any sample statistic that is in the tails of the sampling distribution will result in a confidence interval that does not include the population parameter. That was not what was colored in here on our scale. Okay, so we need a method for constructing any confidence interval, because the one I have up here for you is just for a 95% confidence interval. So we have this crazy formula right here. You're going to need this. So let's go ahead and put a little cloud around this guy. We are going to find this interval. what you will do is you will find the following things. You will find what's called the critical value. You will also find the standard deviation. That's all that this is a critical value multiplied by the standard deviation. If you already have the number for standard deviation, you can just multiply by that instead of doing this crazy formula, although it's not hard because we have a calculator. So this value, z sub alpha divided by 2, is called a critical value of the distribution. That's going to be huge for us right here. It represents the number of standard deviations the sample statistic can be from the parameter and still result in an interval that includes the parameter. This table will be your best friend. Let's put some stars around it. These are the commonly used confidence intervals and the commonly used critical values. I'm going to teach you how to find critical values in case it's a confidence interval that's not 90, 95, or 99. But look here when you're looking for a z sub alpha divided by 2 because this is easier. Okay, so we're going to come back to this table eventually. Okay, let's start building this up. It feels like a lot, and then you're going to see an example, and it's okay. I'm giving you a lot of information here at first. The interpretation of a confidence interval. A percentage confidence interval indicates that 1 minus alpha times 100% of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains that parameter. We're going to highlight these next couple sentences, though. It says, it is extremely important, or an extremely important point is that the level of confidence refers to the confidence in the method, not in the specific interval. A 90% confidence interval, or level of confidence, does not tell us there is a 95% probability that the parameter lies between the lower and upper bound. We're not talking probabilities, we're talking method. The method in which we used, we're confident in. So let's see just a little baby question right here. It says, when that Gallup survey conducted the poll from example 1, 45.1% of those surveyed considered the amount of federal income tax they have to pay as too high, because we got 0.451. Gallup reported its survey methodology as follows. Results are based on telephone interviews with a random sample of 1,015 national adults aged 18 and older. For results based on the total sample of national adults, one can say with 95% confidence that the maximum margin of sampling error is 4 percentage points. Let's determine and interpret the confidence interval that they used. Okay, what is the proportion here? What is p hat? Sample proportion. 0.451. Fabulous. Let's make sure that we have satisfied the 3 requirements to use p hat. Number 1, is it randomly sampled? Check. Number 2, is it independent of each other? To check independence, we just had to make sure that our sample was less than 5% of the population. We did this last time. About how many American adults are there?
A million.
We were in the billions, right?
Yeah, 300 billion.
Is this less than 5% of them? Yeah, so we're good on independence. Then we also just need to make sure our sample size is okay. And again, you would do the n times p times 1 minus p. It has to be larger than 10, and we're good. We would check these 3 things. The next question is to find our error. In this problem, they told us that we would have a margin of sampling error as 4 percentage points, which means this is going to be 0.04, 4%. So we are 95% confident that the proportions of Americans aged 18 and older who believe that the amount of federal income tax they have to pay is too high is between something and something. All we're going to do is do the sample proportion plus your error and the sample proportion minus the error. When we do 0.451 plus 0.04, we get 0.491. Do you agree? We're adding this number and this number. That's going to be our upper bound of our confidence interval. We'll also subtract the error, so 0.451 minus 0.04411. So we are 95% confidence. What? 0.051? You didn't have enough zeros in your number. We are 95% confident that the proportion of Americans aged 18 and older who believe that the amount of federal income tax they have to pay is too high would be between 0.411 and 0.491. So between 41 and 49%. Our number we actually got from our estimate was 45.1%. Now we have this range of numbers that allows us to be very confident that the actual number is between here, due to our methodology. So how do we actually do this from scratch? Because this was just verifying we understand lower and upper bounds. That's what this next couple boxes are going to help you find. If we're actually constructing a percentage confidence interval for a population proportion, we're going to make sure that a simple random sample is of size n from a population is big enough and also simultaneously small enough, right? Independent. And use the following formulas. Let's put little clouds around these guys. These are going to be important. Okay, our lower bound is p hat minus z sub alpha divided by 2 times the square root of p hat times 1 minus p hat over n. Upper bound is exactly the same except for what?
Plus.
We have a plus. Now, what I also find easier to do is actually split this up because that's a whole lot of letters floating around there in a formula. I actually like to come down here and do this first. The width of my interval is determined by what's called the margin of error. The margin of error, or capital E, in the percentage confidence interval is what you're adding and subtracting each time. So I find it easier to calculate my error first, kind of like we did in this problem above, because then I simply have to add it and subtract it from p hat. So the complex formula is there if you wanted to write down one thing, but it's actually easier, in my opinion, to start here and then just subtract for the lower bound and add for the upper bound. You ready to see one all the way through?
No.
It's really not that bad. There's a lot of info going on here. Trust me. Okay. This is also a very pointed example I picked for you guys. In the parent-teen cell phone survey conducted by the Princeton Survey Research Associates International, 800 randomly sampled 16 to 17-year-olds living in the United States were asked whether they have ever used their cell phone to text while driving.
It's not driving.
I'm side-eyeing all of you right now.
This.
Be good.
You don't see my car in the driveway, do you?
I don't leave this building, so no. Hold on, let me go answer the phone. Let me go answer the phone while y'all think about your lives for a second.
Right, you live-
Okay, so step one, when you're asked this question, sorry, I guess I didn't even finish reading the question. Of the 800 teenagers surveyed, 272 indicated that they text while driving. I think it's higher because y'all need to stop texting while driving. Obtain a 95% confidence interval for the proportion of 16 to 17-year-olds who actually text while driving. Okay, step one, if this was asking you to do this question, these are the things that you do. We're going to compute p hat. Great. P hat is easy. It's 272 out of 800.
How many decimals?
Just 2.
Okay.
0.34.
Oh.
Step 2, we had to make sure we can use the rules that we're using. Verify the data was obtained through a simple random sample. Are we good? Do we see these words, random sample,
Where?
in the blurb?
Yes.
Right here. Randomly sampled. We're good. The second thing we have to check is we have to verify the normality condition, that the sample size is large enough. n times p hat times 1 minus p hat needs to be greater than or equal to 10, so let's do this real quick. The number of people surveyed is 800. P hat we just found to be 0.34, so 1 minus p hat is 1 minus 0.34. Somebody in their calculator, what is that number rounded to 2 decimals? Sure.
179.52.
It should be 181.99? Question mark? I don't have a calculator over here. Is my math off?
I got 179.52.
That's what he got too. So my math was off. 179 point, say again? 92? Is it 52?
Yes.
Either way, is that larger than 10?
Yes.
Okay, then that condition's fine. Then we also have to verify the independence condition,
Oh, yeah.
that this is less than 5% of the total population. What we're surveying 800 people, is that going to be less than or equal to 0.05 of the entire population of teenagers, 16 to 17-year-olds in the United States? Yeah, because I'm literally just going to put a lot.
Oh.
That's fine. That's a small enough survey size where we're not getting close to 5% of the population. Remember, U.S. population is in the billions, so 2 age groups is probably still in the billions. Okay, check. Good. We now can use the formulas that we put little clouds around on the other page. So we do them in this order. We're going to determine the critical value. Most of the time, the critical value you're using is on that cute table we also put stars next to. But in case it's not, let me show you how you do this. What confidence interval are we trying to find? Read the question. 95%, which means that my alpha is 1 minus 0.95. 0.95, 95%. What is 1 minus 0.95? 0.05. Now I need to divide that number in half because I'm trying to find z of 0.05 divided by 2, which would be z of 0.025. The number that's in the subscript is what you're looking for to be the probability to the right of that z-score. So we go to our formula, our pink paper. We find 0.025. You guys did this earlier.
Oh, yes.
What was the number we found earlier?
Negative 1.96.
And so if that's to the left, what's to the right?
Oh, that's the 975. No?
Which would be 1.96. Again, percentage confidence interval gives you alpha. Divide alpha in half, and that's the z-score you're finding to the right of.
Okay.
So your table always does to the left. So you have to flip it over to do the right. Or the lower and upper bounds, that's what we're determining. However, like I said, my recommendation is that we do the error first. So to determine the margin of error, that's big E.
Miss, why'd you write your E like that?
Why would I write my E like that? That's how I always write my E's. The formula is z of alpha divided by 2 multiplied by the square root of p hat 1 minus p hat over n. Well, guys, we just found the critical value in the problem before this. What is my critical value? 1.96. Then we're going to multiply by the square root of p hat. What was p hat?
Oh, that's not
0.34 from the beginning. 1 minus 0.34 over my sample size, which is 800. Throw that in a calculator, please. We're going to round to 3 decimals here. 0.033. Awesome. So we have our margin of error. This means that we can very easily do our lower and upper limits. The lower limit of the confidence interval is p hat minus e, which means we're doing 0.34 minus 0.033. Should get 0.297. No, I'm looking at the wrong example. My bad, 0.307. Then we do the upper bound. So p hat plus the error, 0.34 plus 0.033. The correct example was quickly 0.373. So our interpretation, what we learned here is that due to this survey, where we got 272 of you guys to admit that you actually text while driving, even though I'm afraid that that number is higher. So we're 95% confident that the proportion of 16 to 17-year-olds who text while driving is actually between this value and this value. So the steps were, again, we find p hat, we make sure the three things that we have to verify, determine the critical value, probably from the table, find the error, add and subtract the error. Easy, yes? So let's change in this problem. Instead of estimating a 95% confidence interval, let's figure out what happens for a 99% confidence interval and how that compares. So step one, well, we've already found p hat because that didn't change. It's the same p hat from above. It's the same sample, so the three things are still verified. Boom, boom, boom. We're on to step three, which is really step one here. Determine the critical value of a divided by 2, alpha divided by 2, for a 99% confidence interval. Z of alpha divided by 2 does end up being 2.575. Again, we could go through finding that on the table, but these are your commonly used confidence intervals. So we go with that. Boom, step 2, determine the lower and upper bounds of the confidence interval, which means we're going to start with the margin of error. Margin of error is that Z sub alpha value multiplied by p hat, 0.34, times 1 minus 0.34, all divided by 800. Our margin of error becomes correct. So, just before we go on, which had a larger margin of error? This one has a larger margin of error. Keep that in mind. Okay, let's find our upper and lower bounds. Blee, blee, blah. So we'd have the p hat minus the error, which is 0.34 minus 0.043. Yeah, this is the one that's 0.297. And then p hat plus the error, 0.34 plus 0.043, 383. So if we compare those numbers, comparing our lower and upper bounds, what do you notice?
Numbers.
Comparing this lower bound to this lower bound, what do you notice?
Oh, it's, that one's small.
What about this one to this one?
That one's big.
That one's bigger. Interesting. So our interpretation here is that the margin of error for a 95% confidence interval that we got in example 2, 3. Example 3 was 0.033. Increasing the confidence to 99% increases it to 0.043. Then we notice that my upper and lower bounds, the lower one got smaller and the upper one got bigger. So we now have a wider confidence interval. So as we increase our confidence interval, we're allowing more numbers to be a part of this range or this interval to allow us to be more confident that our answer is there. So right there, we saw the effect of changing the confidence interval. Changing the percentage number makes the confidence interval wider. So shortening your confidence interval makes it narrower. But what happens when we change some other things? The effect of sample size on margin of error. So let's say that we actually sampled 1,000 people for this survey. What's going to happen to our margin of error? It will get smaller. As sample size increases, the margin of error decreases. Why do we think that's the case? More random people, more part of the population being shown in that study. Great. This means that the larger sample sizes would result in a narrower confidence interval. So a question researchers might like to ask is, what sample size do I need to be able to easily estimate a population proportion?
An equation.
Here's our two equations. We have two options for this equation. The sample size required to obtain a percentage confidence interval for P with a margin of error of E. So let's highlight some things. Margin of error, E, okay, is given by the following. If P hat is a known prior estimate, so if we know P hat, we use this guy, which says to do the N is equal to P hat times 1 minus P hat multiplied by Z, your critical value, Z sub alpha divided by 2 over the error squared. This is just that other formula solved for N, by the way. We'll multiply by, or divide by, multiply by E. Divide by E. Oh my gosh, you get it. If you don't know a prior estimate, meaning we've done no research whatsoever, we're starting from scratch. If no prior estimate is available, we switch formulas and we just use 0.25 times the critical value over the error squared.
This we don't have P hat.
That's if we don't have P hat, correct. So let's see what this looks like and what the difference is here. An economist wants to know if the proportion of the U.S. population who commutes to work via carpooling is on the rise. What size sample should be obtained if the economist wants an estimate within 2 percentage points of the true proportion with 95% confidence? Part A, 90% confidence. Did I say 99? You get it. The economist uses the 2009 estimate of 10% obtained from the American Community Survey. So if this has already happened, that we use a prior estimate, we're using that first formula. In that first formula, we needed P hat. This is P hat, 10%. In which case, we just straight up fill in that formula. N is going to be equal to P hat, 10%, times 1 minus P hat, multiplied by the critical value. Ooh, flip back to that table. What is the critical value for 90% confidence interval?
It's that one number, right?
Sure.
1.645.
1.645. And then we need error. Where do we get that from? It's this part of the question.
2%.
Within 2 percentage points, so 2%, 0.02 squared. Do we see where all these numbers came from? P hat, because they gave it to me. The critical value, from the table. Error, they gave it to me. We calculate. I would use the fancy fraction. I would use all these parentheses. I would make sure you're squaring the correct thing. And our sample size, to have this 90% confidence, would be 608 0.8556. Now, because this is a population size, we always round up to the next integer,
So 609.
which means 609. We would have to survey 609 people to have this level of confidence within 2 percentage points. But what happens if the economist doesn't want to use a 2009 estimate because it's 2025 and that's an old estimate? So they don't have any prior estimates to use.
So the other one?
So we switch formulas. This time we're using the n equal to 0.25 times that critical value, which you guys already told me was 1.645, divided by the error, still 0.02, squared. What number do we get here?
1691. Yeah, 1691.
265. So question, we're not rounding, we're rounding up. This is a ceiling function, is technically what it's called, meaning this actually rounds to 1692. Not rounding, rounding up. The 5 or more raise the score rule works for everything when you're told round up. And this makes sense because if we have to have at least 1,691.2 people, you can't interview 0.2 people, you're going to you do the whole person.
Okay.
So you round up because it's sample size. So it makes sense why we just straight up round up. Don't round down ever for this, round up for sample size. Now question, what's the difference here?
Action?
Like in general, which one required more?
The second one?
The second, if we don't have a prior estimate, we have to survey like more than double the amount of people. So that's something that surveyors take into account when they're doing inferential statistics, because it is going to be a lot easier to survey 609 people than 1,692. So not having a prior estimate is always going to make your sample size required much larger, usually doubled if not more.